A lot of what we've talked about with topological aspects of graph theory has so far focused on planar graphs. That is, those graphs for which there's an injective drawing into the plane. That is an embedding of the geometric realization of the graph, which lived up in Rn, into the plane. And that's fun, but sometimes you can't do it. Sometimes you can't find an embedding of a particular graph, and there's going to be some edges that cross. A natural question to ask is, how many crossings will there be? This minimum number of crossings that you can end up with is called the crossing number. And so we saw this example to start early on was if we have K5, this is the way people often like to draw K5, like a pentagon with a star in it. And if you're a little bit more clever, you could draw it with exactly one crossing. And this is a satisfying drawing because it highlights the fact that this is really a minimal example of a non-planar graph. That it just has this one crossing. And actually, if you got rid of any one edge, you would get rid of the crossing. So starting with a drawing that has 5 crossings, by rearranging the drawing, by taking a different drawing, I get fewer crossings. And you can ask, how few can I get? All right. So in order to do this properly, we have to be careful about what kinds of drawings we allow. All right, so this definition is going to look a little weird at first, but hopefully it will make a lot of sense in just a moment. So we're going to say that a drawing, remember this is some kind of continuous map from the geometric realization into R2. Drawing means it just has to be continuous. It doesn't have to be injective. We're going to say that a drawing is non-degenerate if it has these 2 properties. All right, and what are they? They are the following. First is that for all points in the plane, if I look at the preimage of that point under this drawing, that there's at most 2 points in the geometric realization. That is, really at most 2 points overlap, or 2 points cross, if you will, at any point in the plane. So that's going to allow us to disallow any drawings which say pile up a lot of crossings all in one spot in the plane. And the other condition here is that if I look at any point in the image of, I've written this as 5e, this is, well, what is 5e? 5e is the restriction of the embedding to just the vertices. So if I just look at where the vertices in the geometric realization go, that's 5e. And so for any point that is in the image of 5e, this one, the preimage can only have 1 point. It has to have at least 1 point because we chose it to be the image of a vertex, but there can't be any crossings at a vertex. And there's 2 kinds of bad situations that this condition avoids. The first is it avoids having 2 vertices land on the same spot. It also avoids having a vertex land right on an edge. Okay, so neither of those 2 things can happen. So you might also notice that this looks a little bit like an equivalent definition to being injective. That is, injective functions have this property that the preimage only has 1 point, but if we just required 5e to be injective, we would only get the rule that no 2 vertices land at 1 point, but this gives us also that no vertex lands on an edge. All right. So the crossings, we can say what a crossing really is now in a non-degenerate drawing, are those points x such that, well, the preimage contained more than 1 point. Right, so and because it's a non-degenerate drawing, we know that it's exactly 2. And the crossing number of G is the minimum number of crossings of any non-degenerate drawing of G. Actually, let me draw a more elaborate example to see what we mean when we talk about this preimage condition. I'll write it again here. We're saying that there's a point here in the plane whose preimage has two other points. So let's draw the plane down here. And let's draw our geometric realization of our graph up here. Let's just take K4 as an example. I think this will work. If I draw it too symmetrically, it could look bad. So we take this embedding here. Let's just take a linear embedding. All right, and the graph we said was K4, and this is up here in 4 dimensions. You could do it in 3D even. So that makes sense. So these don't cross up in R4 where the geometric realization lives, but down when I project them this way, this particular drawing has a crossing. And if I were to look back at that crossing, that is, I were to look back upstairs in high dimensions, I would see that there were these two different points. So this point here is x, and these 2 points here are the preimage of x. So this crossing came from there being 2 points in the geometric realization that hit the same point in the drawing. So we'll use the following notation. We'll say that the crossing number of G, we'll denote it here as CR of G. And let's just write down something that's hopefully obvious at this point, which is that the crossing number of G for a planar graph is equal to 0. To check that this is true, we observe that the embedding, the planar embedding, not just a drawing because it's planar, there exists an embedding, is non-degenerate. Any embedding of a graph into the plane is going to be non-degenerate because it's injective, so the preimage of any point is at most 1, and so that satisfies both our conditions right away. And so it's non-degenerate and has no crossings. There are no points for which the preimage has 2 points. And also that just corresponds to our intuitive notion of what a planar graph is, namely that there are no crossings. So now we can use this definition to state something which is not so difficult to believe, but to work it through the formalisms hopefully will be enlightening. So the statement we want to prove here is that if I take a subgraph, that the crossing number of the subgraph is always going to be less than or equal to the original graph. Okay, so formally G is a subgraph of H, then the crossing number of G is less than or equal to the crossing number of H. If we want to reason about this, we start with the crossing number of H. In particular, we look at the drawing, the non-degenerate drawing that minimizes crossings. So F is really that map that gives us the minimum number of crossings for H. I'll write it like this to the plane. And we know that if G is a subgraph of H, then we have a graph homomorphism, an injective graph homomorphism from G into H, and that induces an injective continuous map from the geometric realization of G into the geometric realization of H. So let's call that little g. And now my claim is that first, F composed with G is a drawing of G. That should be clear here. I just take the geometric realization of G apply G, then apply F, and I land in the plane. This is continuous, so the whole thing is continuous, then it's a drawing. Next, I want to check that this composition is non-degenerate. So if I look at the pre-image, F compose G pre-image of some point x in the plane, that is equal to, actually I'm looking at the size of the pre-image, that is equal to taking the pre-image with respect to G of the pre-image with respect to F of x. Right, because I took a point here, x, I took its pre-image, which was a set of points here, and I took the pre-image of this set to get a subset over here. And this then must be less than or equal to the size of the pre-image of x. And the reason is simply that this map is injective. And so if you have an injective map, the size of the pre-image is less than or equal to the set you're taking the pre-image of. Next, if I want to look at the image of this drawing just on the vertices. So F compose G sub V, by definition, that is F of the image of GV, which is a subset of the vertices in the original drawing. Right? So the drawing we started with of H. And this is really just our way of expressing clearly that when you take this composition, this drawing of G that goes from little g through F, that all the vertices land on the same points where vertices landed from H. And so from these two facts, it's pretty easy to check now that F compose G is itself non-degenerate. So now I have a non-degenerate drawing, and it also has this property that crossings in F compose G are also crossings in G. Right, that follows just from this fact up here. And so the crossing number of G is going to be less than or equal to the number of crossings in F compose G, which is less than or equal to the number of crossings in just, this should be F, the original drawing. And so the crossings in G are at most the crossings for H. Let's put some kind of bound on the crossing number. This is the most maybe trivial bound you can prove, but it allows us to put our knowledge to work. So I claim that the crossing number is less than n to the fourth. So there's always a way to draw a graph G, no matter what the graph is, where n here is the number of vertices. I can draw it with at most strictly fewer than n to the fourth crossings. And the way I'll do it is just consider any linear embedding. Actually, sorry, I shouldn't say embedding. Any linear drawing that has the following property: no three vertices are collinear. That is, the images of the vertices. So if I have this property, then it's not hard to check that the drawing will be non-degenerate. And every pair of edges intersect at most once. Because it's a linear embedding, we can appeal now to the geometry of the plane, two line segments, for points that have no 3 points collinear, there can be at most one intersection here. So for every pair of edges, I can get at most one crossing. So crossing number of G is less than or equal to M, choose 2. And recall that the most edges you could possibly have in a graph is N, choose 2. So crossing number of G is bounded by N, choose 2, which is less than something like, well, this is less than N squared. Choose 2, which is less than N to the 4th. Now, this seems like a really crude bound as far as an upper bound, and it's not immediately obvious that there are graphs which require crossings that asymptotically look like N to the 4th. In fact, it's a little bit tricky to get bounds that are asymptotically close to this. And it's natural that the kinds of graphs you would look at would be, say, the complete graphs. But in the next video, we'll see some specific ways of proving lower bounds on the crossing number. And you'll see that actually it can be, asymptotically at least, it can be this bad. But before we get to that, we should map this crossing number idea into the world of graph invariance and prove that this crossing number really is a graph invariant. So remember, for graph invariant, that means we're going to show that if the graphs are isomorphic, then the invariants are the same. So let's suppose we have some isomorphism between two graphs, G and H. This is an isomorphism, therefore it's injective. And if we were to go through the proof for subgraphs, it wouldn't be too much of a change to see that it didn't actually use the fact that it was a subgraph. It just required us to have an injective homomorphism. So if you have an injective homomorphism from G to H, that implied that we had this inequality on the crossing numbers. Similarly for the inverse, so if there's a isomorphism, it means there's another isomorphism going from H to G. And this one is also injective, and so that implies that the crossing number of H is less than or equal to the crossing number of G. And since I have these inequalities in both directions, I get that they are in fact equal. Now something even a little stronger than this is true. So this crossing number is not just a graph invariant, it's also a topological invariant. And that means for graphs, the geometric realization of G, if this graph's geometric realization is just homeomorphic to some geometric realization of some other graph, then that also implies that their crossing numbers are the same. Okay, I'm not going to do this out in the video. It almost works exactly like the proof we did for subgraphs, except you do have to be slightly more careful. And let me just show you what goes wrong if you try to just take a drawing, a non-degenerate drawing of H, and look at how it gets composed with this homeomorphism. So it could be that two edges in the drawing of H have a crossing here, and it could also be that G is a subdivision of H. We know that subdivisions of graphs are still homeomorphic. And it could be that if I push the drawing of H that I have here through that homeomorphism, the subdivided edge, it might land right on the crossing, which would cause the new drawing to be degenerate. And so you do have to be a little bit more careful to show that it's a topological invariant, but it's, again, not too hard to do. And the result is that we have another topological invariant. Remember, the other one we had was the Euler invariant and the Euler characteristic for planar graphs. So these are other topological invariants of graphs.